All right, so let's wrap up this section, the derivative as a function, with an exploration of the derivative graphically. So I want to spend some time looking at the derivative graphically in this video and getting into this piece, this caveat that we've been carrying around. And we've talked a little bit about this on a previous example with some graphs, but I want to spend a little bit more time talking about that, as well as the connection between continuity and differentiability. So it's quite a mouthful to say that word, differentiability. But that's what I want to spend some time on this video doing. But just to start us off, I'm just projecting again the definition of our derivative. So we want to remember that the derivative is by definition a limit. It is a limit of this difference quotient, which represents the slopes of tangent lines. So again, this is always talking about graphically when we get into, which is what I want to spend time on this video doing. This is graphically representing the slopes. This new function we're creating, this function called the derivative, is graphically representing the slopes of tangent lines to the curve y equals f of x. So keeping that all in mind, that's what we're working with and that's what we're starting at. But let's go over to Desmos now, and I want to show you a fun little applet that I will also link in Canvas that you can adjust the function if you want to, where we can really see the connection between those slopes of the tangent lines and the graph of this new function called the derivative. So let's jump over there, pause the video, and I will open up again in Desmos. Okay, so what we're looking at here is a function that has been graphed. It is actually it's sine of x plus 0.3x, just creates a nice function that we can see some really nice behavior on this graph. And so we're just going to use this graph. And what this applet's going to do, what you can see right now graphed is you can see a point plotted here on the far left of the screen here on the blue graph, which is our y equals f of x. You can see a purple point plotted, and then the red line through that point is the tangent line. So this red line right here is the tangent line at that point. And right now we're at like a equals negative 12.3. So, just it doesn't really matter. We're going to slide that along, but we're a little to the left of negative 10 for the x value there. So you can see the actual tangent curve, and then right above that, what you're seeing here in this red that I keep highlighting, this red right here, this red dot is the actual size, like the slope, the actual numeric value for the slope of that tangent line. So obviously what you can see right here, you can see a line that has a positive slope. The tangent line has a positive slope. And you can see that this red dot, if we were to plot that positive slope at this point, you can see that that is also positive above the x-axis. I mean, I don't know. It looks like it's it's between 1 and 2, a little closer to 1. Okay. And so I'm going to slide this along, and I'm going to stop at some key points as we go on this curve. So as I slide this along, you can see right there we're starting with a positive slope. And now notice that my tangent line, as I'm moving my value here, notice that my tangent line is getting less steep, which is making the actual value of the slope also get a little smaller. It's approaching 0, and then boom, right there, we have a place where we have a horizontal tangent line, and that horizontal tangent line will give us a slope of 0, and that's what we're seeing right here on the graph. We can see that slope of 0. Now notice, as we continue to slide our A, our tangent lines are going to have negative slopes. So you can see the tangent line is dipping down now with a negative slope, and it's getting more and more negative, so it kind of hits a peak. Notice what is also happening with our dot right above that is plotting, essentially. It is plotting our actual numeric value for that slope. And so it's a little below the x-axis with a negative slope. And then notice that the steepness of the slope still negative, but see how it's getting less steep till it hits a 0 again. So right, if I can get it, I'm kind of trying to get it exactly on the 0, but right about in there we have another horizontal tangent line, and a horizontal line has a slope of 0, and so we're having another place where our slope is 0. We're hitting the x-axis again with that red dot, and we keep going, and notice again positive slopes, and then they get smaller, less positive, hits a 0, they go negative, then they hit another horizontal tangent line, then they go positive, and up and down and up, and so we're seeing that with that tangent line as we do that slider. So now what I'm going to go ahead and do is I'm actually going to graph the derivative. I'm going to graph f prime of x right now. And so that's going to show up on our screen here in black. So what is being graphed right here in black on the same graph as our actual function? The function itself is in blue. The tangent lines are here in red. And the actual derivative, f prime of x, is this black line. And so notice what happens. Now as I slide it, you can see not only can you see the numeric value of the slope going positive, negative, and 0, but you can see it actually plotting a function, which remember the derivative is a function, and that's what we're looking at here. So there you go. You can see that slope of 0 coming in there right there when it crosses the x-axis. Then you can see those negative slopes. That's plotting as negative values on the derivatives graph. And then you've got your positive slopes again, and then your if I can get this, it's touchy with a mouse. Get it right there. You can see that horizontal tangent where it's crossing, the derivative is crossing the x-axis again because it has a value of 0, and then negative, and then 0, and then positive 0. And so you can see that. You can actually drag this along as you go. And what I'll do is I will actually go ahead and put this this little Desmos code, this link to this Desmos in Canvas so that you can come in here and you can play with it. I will also tell you that you can adjust the f of x if you want to put in a different function. You can type in a different function and explore what the derivative graph looks like for those other functions. All right, I want to show you just one more before we go, because for this particular one, the derivative, the slopes of those tangents are defined for all values across this range that we're looking at, the domain that we're looking at here. But let's look at one maybe where something different happens. Okay, so here's another function. This is the absolute value of x. So graphed in blue, just like the previous curve had been graphed in blue, is our actual function. So this blue curve right here that we're looking at, that is simply the absolute value of x. So we're looking at the function absolute value of x. And notice that we do have a tangent line. It's actually being plotted out here. I'm going to pull it in a little further. We do have a tangent line. There we go. So the tangent line, it's hard to see. It's kind of, well, right now, like when I just took it off, you can see that there's actually a red line being laid on top of the blue line for the absolute value. And that is because the slope of the tangent lines on a line are just exactly the slope of that line. So obviously the absolute value is made up of two lines, negative x when x's are negative and positive x when x's are positive. And anytime we plot the actual slope, the tangent line, and we look at the slopes of the tangent line, it's going to be the same as the actual line. So as I slide my A here, you'll notice that not only we are plotting tangent lines, Desmos is plotting tangent lines, but they're right on top of the absolute value function. So they are actually being plotted right on top of the absolute value function. You will notice also, as I'm kind of going back and forth on this negative arm, I guess, of this absolute value, the negative x portion of it when the x's are all negative, you will notice that the slope is at a -1. Down at the bottom, you see that little red dot that is at -1 for all those values. Now, something really interesting happens right there. Right here, we go from having a slope of -1, and if you don't watch really closely in this video, as I slide, boom, all of a sudden, there is no tangent line. Notice the red line has disappeared. We cannot graph a tangent line at that point 0. And that goes back to the definition of the tangent line. The definition of the tangent line says it's a limit as h approaches 0 of f of x plus h minus f of x all over h, which is representing the slope of a secant line, and you have to be able to do it from both sides. So if all of a sudden we go from having a slope of -1 and in an instant we switch to +1, which is what's happening right here, then at that point where it switches, that limit does not exist because the slope from the left side is -1, boom, hit that corner, and now the slope on the right side is +1. And so right at 0, the derivative does not actually exist. This is what we call mathematically a corner. When two lines like this come together and make a sharp corner, we call it a corner. But the derivative itself does not exist right here. And so I wanted to point that out. If we were to actually graph the derivative, and I'm going to go ahead and do that. If we were to graph the derivative, and then I'll run my slider again. So again, notice here, there's that slope. All those slopes are -1. All of a sudden in an instant. Now, we don't have this zoomed in enough to see like an open circle, but there's actually an open circle on the derivative, both parts of the derivative. And then right there, we pick up again on the right side of 0. The slopes are all 1 now moving forward. The slope of the tangent lines are all 1 as we move along as x continues to increase here. But right at 0, the derivative does not exist, and we have open circles on the derivative curve. So there is a place where the derivative does not exist. If we have a sharp change in the slope, if it changes all of a sudden like it does in this absolute value from -1 to +1, then we say the derivative doesn't exist. That limit doesn't exist. It can't exist if the left-hand side of the limit doesn't equal the right-hand side of the limit. That goes back to our knowledge of limits and all the work we've done up to this point to build our limit tools. Okay, I'm going to just slide this just so you guys can see what this Desmos looks like. I'll slide this over here so you can sort of see the code here. And if you want to, this is where you can just change the function. So you can come in here, you can change that function. You know, if you wanted to look at the sine of x, for instance. Oops, it didn't like my sine of x. Let's see if I can get it to. No, it's not liking my sine of x. But you can put in, whoops, equals, what am I? There we go. You could put in anything you want here. So I think it's because I'm using the keypad inappropriately or something. Maybe if I go sine, well, maybe it's because I capitalized it. Normally Desmos, sorry for that little glitch there. Normally Desmos knows what I want and it does it for me. There you go. Somehow I had a capital S and it wasn't recognizing that as sine of x. I must have accidentally capitalized it. So you can do any function you want. So I just changed that absolute value of x to the sine of x, and now I can explore what the derivative of the sine of x looks like, what the graph of the sine of x looks like. Okay, so let's go back and let's formalize a little bit here with graphs on the notepad. Okay, so let's talk about the connection between continuity and differentiability. And let's spend a little more time looking at graphically, how do we graph the derivatives, and when is it that a derivative doesn't exist, right? By that limit definition, when do those limits not exist for our derivatives? So we just came over from Desmos, and I wanted to also mention that in the ebook, in the Stewart ebook, there are some interactive applets within the ebook that you can play around, and you can also see this connection between a function and the graph of a function and the graph of its derivative, as well as explore the connection between continuity and differentiability. So let's start with this. We have a theorem that actually says if a function is differentiable, it is continuous. Okay? So differentiability implies continuity. So if a function is differentiable at a point on an interval across its domain, whatever that might be, then it is continuous. Now, this is kind of the big caveat, and I outlined it actually down below. This is not both ways, okay? Just because a function is continuous, we don't necessarily know that it is differentiable at a point, on an interval, whatever it might be. So being continuous does not guarantee differentiability. And so I wrote here, show an example, absolute value. We just looked at the absolute value. I just redrew it here so we could talk about it. This function is continuous everywhere because at every single point, and there is a limit, so just real quick, let's make a little note here. Note that the limit as x approaches 0 of the absolute value of x is in fact 0. And therefore, this function is continuous. There's that one place, that one breakpoint that we'd have to be concerned about. Remember, absolute value is actually a piecewise function. So let me write that here. I jumped right into the breakpoint, but there's a breakpoint at 0. If x is less than 0, if x is greater than or equal to 0. So absolute value is, by its definition, it is a piecewise function. So we should consider what happens right at that breakpoint. And at that breakpoint, the limit itself is equal to 0, which is the value of the function. Therefore, it is continuous on the reals. The absolute value is continuous everywhere, from -infinity to infinity. But on the previous video over in the Desmos applet, we showed that if we were to actually graph this, right? And here, let's go ahead and graph this using, rather than using our technology, let's just graph it by hand. The slope of the absolute value for all of these points, the slope of the tangent line at all of these points, and if I were to draw a tangent line, it would lay right on top of the actual absolute value function, but the slope of all those points is -1. So I didn't put a scale here, so I'm noticing that my actual graph is slightly off of 0 there, but you get the general sense. So if this is our function, then our derivative I'll graph in red, would look like this. Now, right at 0, we have a problem because it goes from having a slope of -1 to instantaneously, right on the other side of 0, for all values just infinitely to, infinitely small space to the right of 0, have a slope of +1. So if we were to graph all of these points, so those are just the horizontal lines, -1 and +1. This is my derivative. I could actually write that dy dx. Remember our different notations just a little earlier in this section. So you could write it like that, or you could write it like that, y prime, any way you want to. I didn't describe this as a function. I just called it y. So I'll use Leibniz notation and then Newton's notation just with y prime. So notice on this guy that the function itself is continuous on the reals, but it is differentiable, but y equals the absolute value of x is differentiable. You can only take the derivative. I should say there is only one point you can't take the derivative. I was trying to talk and write and I misspelled. Differentiable, it's a mouthful. It is differentiable on the interval from -infinity to 0 and from 0 to infinity. It is not differentiable at 0. Okay? This function is not differentiable at 0. So notice here that it was continuous everywhere, but there was a point where it was not differentiable. So just because it's continuous at 0, that doesn't mean that the function will be differentiable there. Now, the other direction, if it is differentiable everywhere, then it will be continuous. So you got to just kind of remember on this connection between continuity and differentiability that if it's differentiable, then of course it's going to be continuous. So if a function is differentiable, if we can take the derivative and calculate the derivative function using that limit definition, then it will be continuous. It's not, just because it's continuous, right, doesn't necessarily mean that it will be differentiable. Okay, so if we're not continuous, then a function is not differentiable. So we have that as well. And some reasons why a function would not be differentiable at a point are listed here, and we have explored a few of these, and I'm going to spend a little more time exploring these in a couple of graphs. We just did the absolute value, and that was a corner. So if we have a corner or a cusp at a point, a corner is a sharp corner like the absolute value, something of that nature, and a cusp is something where you have you're coming up to a cusp in the graph where your slopes are getting really steep, infinitely steep, and all of a sudden they switch and they're infinitely steep in the other direction. Okay? A vertical tangent visually would look something like that, where your slopes get really, really steep, and then all of a sudden they just switch and they start getting less steep on the other side. And then of course, if f of x is not continuous, like if you have a jump or a hole or a vertical asymptote, those will also give us a function that's not differentiable at those points. So if it's not continuous, then it will not be differentiable. Okay, so those are our three possibilities. And let's go ahead and look at a couple graphs. So we already looked at the absolute value. That is what we call a corner. So just to clarify, that is a corner. And so it is not differentiable. So for these examples, I want to go ahead and just list on all of these examples. Let's do two things actually. Let's practice graphing the derivative. So let's graph the derivative of the function and list the values where f of x is not differentiable. So we have done that. I started off with this absolute value just because we'd already explored it in Desmos. So we've already done that here. We've graphed the derivative. We did it in red, and it is not differentiable at x equals 0. We actually did the opposite. We stated where it was differentiable, but if it's differentiable everywhere but 0, then it means it's not differentiable at x equals 0. And it's that sharp corner where we're changing, where our derivative has, our derivative representing the slopes of those tangent lines. Just that limit doesn't exist right there, because from the left side it's -1 and from the right side it's positive. It has that instantaneous change. Okay, so that was one. Let's call that example one. Let's come over here and let's look at this. And this is actually a cusp. So let's call this example two. So this is a cusp. And so when I see a cusp like this is a place. This is what we classify as a cusp. I did a small drawing over when we were talking about places where we might not be differentiable or where we won't be differentiable. And a cusp is one of them. But here's an illustration of a cusp. So just from looking at this graph, we know right away we can say that this is not differentiable, and I didn't even put a number, I just called it A. This is not differentiable, or we should say f of x, since we have a function name. F of x is not differentiable I have to sound that out in my head so I couldn't talk while I was writing. Is not differentiable at x equals a. Okay, so at this place, x equals a, we are not differentiable because we have a cusp. I will just write cusp in parentheses. Okay, so we are not differentiable at x equals a. So then what would the graph of the derivative look like? Let's do that in red. So if we were to be graphing the derivative, what we notice right here is right at a, if we're thinking about what the slopes of the tangent lines look like, and I'm just going to grab my ruler so we can see, if I were to think about what the slopes of the tangent lines are here, they're pretty down here, and you can even see my degree measure. Down here where we start, the slopes are pretty flat, right? They're positive, but they're pretty flat. So numeric values there might be like, I don't know, like a slope of 1, and the arrow kind of almost implies like it's going to keep getting flatter if we kept going. So it's almost like coming up here, we have very small numeric values for the slope. But notice what happens is I draw my ruler along here and I think about my slopes are getting, they're positive and they're getting very, very steep. Okay, and so as I drag this up and I get steep, 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 so steep, right? As we're going up there, they're so steep, they're basically vertical. So I'm just going to pull it off to the side for a second. So steep they're almost vertical would mean that the actual derivative is going to have a vertical asymptote right here. Okay, and we're going to start out with positive slopes, so we're above the x-axis. They were pretty small though, and then they're just going to get ever more increasingly positive, so much so that they're actually have the derivative. This now, by the way, is y equals in red f prime of x. They're so steep that they have a vertical asymptote. Okay. Now, all of a sudden, right, right here at this cusp, and this is why the derivative doesn't exist there, because right there at that cusp, all of a sudden it switches to negative, right? All of a sudden the slopes are now they're very steep still, but all of a sudden my slopes are negative. And as I go, my slopes are negative, 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 negative. These slopes are getting less steep negative, but they are definitely negative. They're all negative, negative, negative. I'm trying to get that ruler right on there. They're negative, 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 negative. They're getting flatter and flatter and flatter. They're getting less negative, meaning, if you want to think of some numeric values, right? Like maybe the slope right here is only a -2, whereas over here it's like a negative, way up here it's like a -50 or something, right? And then up here it's like a -1000, right? So again, that's a vertical asymptote. And so, but it's coming from this direction and it's negative because it's negative. The slopes are negative. So here comes the derivative in red. I'm graphing the derivative in red. And as the x's approach a from the right-hand side, the slopes are getting steeper and steeper and steeper in a negative way. And then as we head out towards infinity here, they're still negative, but they're getting less steep, like they're approaching 0 actually. And so we have a graph that looks something like that. So that cusp gives me a point where we're not differentiable. And then the behavior around that cusp gives me this graph for y equals f of x. Okay, let's maybe do one more, then we'll call it good for this video. So let's take a look at one like this. So if we take one like this has got a discontinuity in it. So notice here at B, right, you've got a jump. This is a jump. I'm going to erase this, but I'll write it for now. This is a jump discontinuity. And so, obviously, if it's discontinuous, it's not going to be differentiable, right? Like there's no way that the slope is, the slopes of the tangent lines are one thing completely different on the left side of B than they are on the right side of B. So we know with that discontinuity, just right away, we know we are going to have a non-differentiable function right there. The other issue we've got on this function is right here. The function is actually continuous right there, but it is a corner. And so at that corner, we're going to have, so this was a discontinuity, and up at A, we had a corner. And so those are the two places where this function is not differentiable. So we would say g of x is not differentiable, I'm going to abbreviate, at x equals a and x equals b. Okay, and so one of those reasons was because it was discontinuous, and the other reason because we had a corner discontinuous at b and a corner at a. Okay, so I'm going to go ahead and erase those because let's actually graph this function. So we know the derivative is not going to, we can't graph the derivative, right? It's not defined at a and b, but it is defined for the rest. So let's talk about what it looks like. So when I'm looking at this real quick on my little corner piece, as I come towards A, I notice that the slopes are positive, and in fact they're a line. And so, I didn't do the greatest job. I just kind of eyeballed it when I was graphing this, but I'm kind of thinking, let's look from this point to this point. It looks like we go up 3 and over 1. So it looks like the slopes of those points are about 3. So I think we can actually, let's go ahead and we can be a little specific here, right? Looks like the slopes are 3, and the slopes are just a 3 for all of those values. Whoops, let's need to do this in red. So this is the derivative I'm graphing now in red. So as I come in here, the slopes are 3, 3, 3, 3, 3, 3, 3. All of a sudden I get to A, and I have a quick change. And on the other side, it looks like we actually go, it's about, well, I don't know. Actually, it looks like I made it a slightly different slope. Looks like we go over 2 down 3, so a negative 3/2 or something. So let's come down here, and all of a sudden we've got a negative slope from here to B. And then we have an open circle at B. And then right at B, think about drawing a tangent line right here, right? Like pull out your ruler. If you draw a tangent line of a horizontal line, the slope is 0. So the slope is 0 for all of those points. So for all of those points from B on, our derivative is just 0. So from B on, the derivative is going to be right here on the x-axis, and it is just 0 because the slopes of all those tangent lines. So now in red, I'm graphing y equals g prime of x, and we can see how it corresponds to the actual graph and the slopes of the tangent lines to that graph, y equals g of x. Okay, so just to end, just to remind us, there are those 3 types of conditions that we want to keep our eye out for graphically, places where the derivative doesn't exist, where a function is not differentiable. So of course, any place that we have a discontinuity, a jump, a hole, or a vertical asymptote, those are places where the function will not be differentiable. Also, if it has a corner or a cusp, and at corners and cusps, the functions are actually still continuous at those points, but they will not be differentiable. And then any place that we have a vertical tangent line, okay? So if we have a vertical tangent line at x equals a, that is also a place where it's not differentiable. So I'll go ahead and leave it on the screen. These are the places where you got to be careful of, and you also want to remember that if it is differentiable, then it will be continuous, but that is not necessarily true the other direction. Okay, please do take a little bit of time. It really kind of helps with the conceptual understanding of what a derivative is and how it connects to its function when we look at them graphically and look at those behaviors in a graph like corners and cusps and discontinuities and vertical tangents. So take a little time and explore that in Desmos and by hand.